Hey everyone, and welcome to This Explainer. Today, we're demystifying the absolute DNA of our digital world, object-oriented programming, or OOP for short. Whether you're a total novice trying to figure out how software is actually built, or you already know your way around a codebase and just want to solidify the basics, we are going to break down some pretty complex software architecture into simple, easy-to-grasp concepts. But right off the bat, I want to throw a question your way. Picture this. It's 2026. Artificial intelligence is basically eating the world, right? It's writing its own code, generating entire applications on the fly. So why in the world are we still relying on a programming paradigm that traces its roots all the way back to the 1960s? Well, the crazy truth is, even with tech evolving at breakneck speed, OOP remains the dominant foundation of software. It isn't outdated at all. It's the bedrock. And to get why it survived and thrived, we really need to understand how it ticks. So here's our roadmap for today. We'll kick things off with a brief history of OOP, demystify classes and objects, dive into the 4 pillars of OOP, check out some real-world applications, and finally, look at how all of this scales into modern software. All right, part 1, a brief history of OOP. To get why OOP even exists, you gotta look at the mess it was trying to fix. Early programming was just a massive, linear sequence of instructions. But developers quickly realized they needed a better way to model the messy, complex real world. Enter the 1960s and Simula. Like the name suggests, it was designed to create simulations of real-world things like factory floors. Then, fast forward to the 70s. Alan Kay envisions personal computing with the Dynabook and helps build Smalltalk, a language built entirely around objects talking to each other. By the 80s, Bjarne Stroustrup takes these ideas, bolts them onto the hugely popular C language to create C++, and boom, OOP hits massive commercial use. Finally, the 90s roll around. James Gosling at Sun Microsystems creates Java, and suddenly, OOP is the backbone of the exploding internet. So it went from simulating simple factory floors to literally powering the global web. Pretty wild trajectory. Moving right along to Section 2, Classes and Objects Explained. Okay, so here's where people usually get tripped up, but it's actually pretty straightforward. You just have to understand the difference between a class and an object. On the left, we've got the class. Think of it like a blueprint at a car factory. Now, you can't drive a blueprint, right? It just defines what the car will have. A specific color, an engine, 4 wheels, and what it will do, like accelerate or brake. Over on the right, we have the object. This is the actual physical car that rolls off the assembly line. It's a real working copy with a very specific state. It's painted red, it has a full tank of gas. The beauty here is that you just need one single class, but you can use it to mass produce thousands of unique objects. Which brings us to Section 3, the 4 pillars of OOP. If you've ever taken a comp sci class, you know these. The famous 4 pillars: encapsulation, abstraction, inheritance, and polymorphism. Let's break them down real quick. First up, encapsulation. Sounds like a big, intimidating word, but you actually deal with it every day. It just means bundling your data and the methods that use it into one single unit, and hiding the messy internal state from the outside world. Think about an ATM. You walk up, use the screen, punch in your PIN on the keypad to get cash, but the complex, super sensitive mechanisms inside, the actual vaults of money, the network transaction logic, are safely locked away in a black box. You absolutely cannot reach in and just manually tweak your account balance. And that's exactly the point. By restricting that direct access, encapsulation protects your data and stops other parts of your code from accidentally breaking things. Next, we have abstraction. While encapsulation is all about hiding data for safety, abstraction is about hiding complexity just to make things simpler to use. Back to that car analogy for a second. When you're driving, you really only need to understand the interface. Steer with the wheel, stop with the pedal. You definitely don't need to understand the thermodynamics of a combustion engine just to go buy milk. Abstraction is the exact same thing in code. It exposes only what the user or another chunk of code needs to see. It reduces your cognitive load and makes the whole system way cleaner to interact with. Pillar number 3 is inheritance. And honestly, this is the ultimate hack for code reusability. Inheritance lets a brand new child class automatically inherit the properties and methods of an existing parent class. See, you have a general animal class that knows how to eat and sleep. You don't want to rewrite all of that code from scratch when you decide to make a specific dog class. The dog simply inherits those traits. It saves developers massive amounts of time and keeps the code beautifully organized according to the golden rule of programming. Don't repeat yourself. Take a look at this Python code to see exactly how that looks. Up at the top, we've got our base class, animal, which has a neat little method called speak. Right below that, we create our dog class, and we literally just pass animal into it right there in the parentheses. Bam! By doing that, the dog immediately inherits all the traits of the animal. But, and here's the cool part, the dog can also have its own unique functions, like that rollover trick you see there. It's the perfect is-a relationship. A dog is an animal, just with some extra specific behaviors bolted on. And finally, pillar 4, polymorphism. It's a Greek word that just means many forms. Basically, it lets a single command or interface act differently depending on the specific object that's calling it. Imagine you have a command called draw. If you tell a circle object to draw, it renders a circle. Tell a square object to draw, it renders a square. You don't have to write these massive, messy if-else statements checking the shape type first. The code just naturally adapts its behavior based on the object, which makes your entire system incredibly flexible. Now, different programming languages tackle this in their own cool ways. Over on the left, C++ uses what's called static polymorphism. Notice how that same library write open function is listed multiple times? But look closely. Each time, it's accepting a totally different type of data. An integer, a file, a character string. The compiler is smart enough to figure out which one to use. On the right, Python handles it with something called single dispatch. The add function behaves completely differently whether you hand it an integer, a string, or a list. It's the exact same interface, but the execution is highly tailored based on the data type. All right, section 4, real-world OOP applications. So, you might be asking, why does all this theory actually matter outside the classroom? Well, look at this breakdown comparing OOP to the older, procedural style of programming. In procedural systems, your data is often global, shared everywhere, and the code is just this long, linear sequence of functions. When a project gets big, that turns into the ultimate developer nightmare, spaghetti code. Everything is so tangled that pulling one tiny string breaks something on the other side of the app. OOP, on the other hand, structures everything into self-contained objects with their own private data. It's super modular. If a bug pops up in the customer object, guess what? It's isolated right there. Debugging and scaling become infinitely more manageable. And because it scales so flawlessly, OOP is literally powering the stuff you use every single day. Finance? Your bank account is essentially an object with encapsulated balance data. Healthcare? Electronic patient records use inheritance to manage security and different user roles. Gaming is a huge one. If you've ever played a game built in Unity, every single character, tree, and item in that world is a game object. And in web dev, massive frameworks like Python's Django or Java's Spring use OOP as their very core architecture, so they can handle millions of users without breaking a sweat. Let's wrap things up with section 5, OOP in modern software. Now, you might be hearing a ton of buzzwords lately, stuff like the cloud and microservices, and you might be thinking, did OOP get left behind? Not even close. Look at this brilliant quote from software architect Thomas Tolka. Conceptually, a service is just an object on the system level. Today, the absolute gold standard for building massive apps is microservices architecture. You split an app into tiny, independent services that just talk to each other over the cloud. A service owns its own data, it controls its own behavior, and it operates completely autonomously. Sound familiar? That is literally the exact definition of an encapsulated object. The core principles of OOP didn't disappear, they just scaled up. We went from organizing lines of code to organizing entire global networks. Which brings us right back to that provocative question we started with. As AI continues to eat the world, cranking out code at lightning speed, how are these core principles going to shape the future? Because the reality is, it doesn't matter if the code is written by a human developer or a machine. Systems are always going to require modularity, security, and logical boundaries, or else they just collapse into total chaos. The blueprint of object-oriented programming, encapsulation, abstraction, inheritance, and polymorphism, is honestly just as vital today as it was decades ago. It is still the best mental model we have for translating our incredibly messy reality into the digital realm. Thank you so much for hanging out with me for this explainer. Keep questioning, keep learning, and I'll catch you in the next one.